Do you have a... Can you hear me this way?
Okay, then, yeah, is that okay? Yeah, or otherwise I can shout more. Okay, yeah, thank you very much. So I'm going to give a very brief overview of the AGE Pro, which is the first systematic survey of gas in protoplanetary disks done with ALMA. But first of all, I want to give a bit of a motivation for this survey. So we know that disks evolve and disperse over a time span of about 10 million years. And we know that both from observations tracing the infrared axis that you can see here as a function of age in different star-forming regions, and we know also from the rate of accreting star as a function of age that also declines with time. Here I want to mention that I've chosen this old version of the infrared axis because in that review we actually make a comparison with bodies in the solar system when they form, and we reach the conclusion that if calcium aluminum reach inclusion, they form in the first million year of disk evolution, then the dispersal of dust in the protosolar nebula essentially follows the one that we see in other disks. But these tracers, both of them, they probe material that is very close to the star. And so it's really with ALMA that we could start. It doesn't work anymore. Let's do this. No, go ahead. Okay, so I will use this. All right, so it's really with ALMA that we could start to probe the bulk of the disk material. Now here looking at the evolution of the dust mass, so looking at millimeter fluxes and converting them into dust disk masses. And so what you start to see here is, although at any time there is a large spread in dust disk masses, there is also a decline with age. So this was the stage when we decided to put together a large program to study the gas with ALMA, because what we wanted to see is what is happening with the bulk of the gas with time. So again, this is a first systematic survey, and I want to mention also the important role that early career scientists played, both in the reduction of the data and also in the analysis and in the publication of some of the results I will be able to mention here. All right, so we decided to go probe 3 different star-forming regions. So you can see here on the top Ophiuchus, row off, which is meant to represent the early stage. And then we have Lupus, the intermediate stage, and then Upper SCO, which is the final disk dispersal. We restricted ourselves to an error range in stellar mass because we know that disk properties are stellar mass dependent. And also we had to bias ourselves to sources which had previous CO detections, because as Dinshan mentioned, the CO isotopologues are some of the best tracers for the disk mass. And if you want to get a large program, you ought to be sure that at least the main CO isotopologue was previously detected. So here at the bottom, you can see the tracers that we chose, so 3 CO isotopologues and also N2H+, because when CO is not present in the gas, so is depleted, then N2H+ is more abundant. So it's a kind of a complementary tracer for the disk mass, if you want. So there is something here. So for the next speakers, if you use this button at the top sometimes, then it gets stuck. Yeah. So I will not use it anymore. Okay. So, so the thing to mention that I want to mention is that the first set of AGE Pro results are out, and there are 12 papers that have been published in August. So first, there is an overview paper that discusses the strategy for the observations and also some of the main results. And then we have a set of papers that focus on measurements of disks in individual star-forming regions. Another set of papers that explain the method and the main results on the gas and dust properties of these disks. Then papers that focus on the comparison between theoretical models and observations, both for the gas and the dust. And then there are two very interesting papers, things that we didn't expect, two discoveries, a potential planet in a disk and also an extreme variability at millimeter wavelengths in one of these objects. So again, I can mention only a few results. So here I want to show a plot looking first of all at the data. So here what you see are normalized fluxes for the different CO isotopologues as a function of millimeter flux for the two star-forming regions, Lupus and Upper Scope. And the first thing you notice here are the similarities of the fluxes, right? And that was the first surprise because we decided to choose Upper Scope to probe the evolution, so we expected some dispersal. But basically from these observations along with the modeling, one of the first results that came out here is that there are similar gas disk masses between these objects in Lupus as well as in Upper Scope. The other surprise for those who claimed that there was a lot of CO depletion in many of these disks before these observations was that N2H+ was actually detected quite frequently in 40% of the sources, which again suggests that CO is perhaps not that depleted. Okay, so this is a nice paper comparing the data with the observations. So let me tell you what you see here. So there are three sets of panels showing the evolution in color of disks where dust is allowed to migrate inward. In the bottom panel, there are no traps for these dust grains. In the middle panel, there are some weak traps. And on the top panel, there are strong traps. The data are the stars. And so you can immediately see that the middle panel is the one that best reproduces all the data, meaning that even if there are traps in these disks, these traps are kind of weak, and so there is some leaking of these millimeter grains, these pebbles, to the inner part of the disk. And I also want to mention that a weak trap in this type of simulations is one that can be induced by a Neptune mass planet in the outer part of the disk. So traps are leaky. Now, this other plot instead is also from a paper that does a comparison of theory with observations, now looking at what is the main mode for accreting gas from the disk onto the star. So the data here are in red, and there are two panels because there are two different flavors, if you want, of models to explain accretion onto young stars. On the left side are theoretical models for so-called wind-driven accretion, where winds extract angular momentum and enable accretion onto the star. And on the right side, instead, what you see are the classic viscous accretion model, where angular momentum is redistributing outward. So the result of the simulations are these black dots, and again, the data are in red. And so one of the main conclusions from this paper is that wind-driven accretion model seem to reproduce better the distribution of mass accretion rates as a function of disk mass that we have measured with H-Pro. I also want to mention that there is independent support from MHD for MHD wind-driven accretion that comes from direct observations of these winds, and Amani is going to talk about them after the break. So since I have no more time, I want to leave this last slide here and just mention that these are the type of measurements that we have from H-Pro, dust disk masses, gas disk masses, ratios, as well as dust and gas sizes. Here are the main outcomes. I mentioned all of the two middle one. The upper one I think is important, so let me tell you. The gas and the dust appear to evolve on a different time scale, and the gas seem to take longer. And I also want to mention the last bullet point, because this is also something we didn't know before. Many disks appear to be small, even in the gas. And external photoevaporation seems to be important in the case of upper score. So when doing this comparison as a function of age, we should also be asking ourselves, is upper score really the right region to compare with low mass star forming region? So that's all I wanted to say. And yes, look at the press release. And also, if you want to download the data, they are all available up on that site that is hosted by our Chilean collaborators. Thank you.
Thank you, Ilaria. Are there any questions for Ilaria? Yes. Shubham has a question in the back.
Hi, Shubham Kanodia, Carnegie Science. My question was regarding the Neptune planets that you hypothesize could cause these traps. Does the frequency of those match what we expect for Neptune-type planets in these stellar masses?
Well, we cannot really do that comparison, right? Because we don't know what is the fraction of stars that have Neptune mass planets at those larger distances where we place these traps with ALMA. So with ALMA, we are sensitive to distances that are beyond the 10 astronomical units, right? And the population of Neptunes that we know of is mostly closer in. So were you thinking about connecting those inner population with the outer population? Ah, okay, I see. Okay, we have not done that that type of analysis. Yeah, but it's an interesting point. Yeah.
Thanks, Ilaria. I'm sure there are more questions, but for the interest of time, the next two talks are going to be online. Let's thank Ilaria again